The arc of what we're going to talk about in this lecture series is various sort of desperate measures to try to deal with the changing climate. And one of the avenues that people are thinking about is to blow smoke up into the stratosphere to sort of temporarily cool things down as a kind of emergency measure. But what I'll show you today is that the CO2 that we're putting into the biosphere is going to stick around for essentially forever, a really long time. And so, blowing smoke up into the sky is kind of like taking an aspirin to treat, a serious, addiction, disease. It sort of like masks the symptoms for a little while, but it's not like a real answer. So the real answer would be to clean up the carbon dioxide, and that's what I'm going to start to think about with you guys today. So I'm going to sort of talk about the natural carbon cycle and the fossil fuel carbon and kind of how it works and the magnitude of the issue. And then another talk by a colleague of mine named Kale is going to, there you are, in a couple of weeks, he's going to talk about ways of cleaning up the CO2. So because the carbon just kind of accumulates in the biosphere and doesn't go away, it's really sort of a waste management issue. And, I don't know a lot about solid waste, but what I know comes from this poem about Cynthia Sylvia Stout, who would not take the garbage out. And so it piled up to the ceilings, coffee grounds, potato peelings, brown bananas, rotten peas, chunks of sour cottage cheese. Forgive me, I was hoping there'd be a bunch of middle school kids here today.
That's a classic book.
It is.
Everybody should read that poem.
So I looked it up, how much solid waste we produce, and tried to figure out how long it would take for Cynthia Stout to, meet her awful fate that I cannot right now relate. So the average amount of solid waste per capita in the US is a little bit short of a ton of garbage per year, 1,000 kilograms, more like 800 something kilograms, so rounding up maybe a ton. And then, how much that's going to accumulate depends on what we call the bulk density of the garbage, which is the, including all the air spaces and stuff. So a fresh bag of garbage in a plastic bag, you litter, throw it on a waterway somewhere, and it might float like halfway out of the water, so like half the density of water. Or you could, if you're living in a house full of that, maybe you stomp it down so the density goes up. But anyway, what I get if Cynthia Sylvia Stout was living in a 1,000 square foot, sort of smallish kind of a house, maybe I'm projecting there, but it might be a couple of inches a year, which just sort of surprised me. I was expecting between ankle and knee high for a year worth of garbage in a house, but a couple of inches. So it would take a while before it started to reach the walls and all of that. But carbon dioxide is also a waste product. And just comparing the mass of the two, this kind of shocked me. I just looked this up yesterday. We emit 14 or 15 times as much carbon dioxide garbage as solid garbage. And that's a fair apples to apples comparison between, kilograms, versus kilograms. CO2 we don't think about as having kilograms because, we don't experience the weight of it directly. But it's a lot higher. And then the next part is not a fair comparison because the other thing about gases is that they're big and puffy, and so they take up a lot of volume. So this next part is just for grisly fun. In a year, if the carbon dioxide that Sarah, Sylvia, Cynthia Stout emitted was emitted in a pure form of CO2 gas in her house. CO2 gas is heavier than air, so if you don't mix it, it would just rise up from the floor until she would meet her grisly fate much sooner than with the solid garbage. It would be a couple of weeks before it would, that would be the end. So in a year, it's like 19 stories. That's how much CO2 garbage each American is littering into the atmosphere every year. I don't mean to preach at you, or be sanctimonious or something, because I know you're here and I very much appreciate that. But that's kind of what we're looking at, is a lot of garbage, gas garbage. So we're, just by background, we're very addicted to this because it's a source of energy, obviously. The energy comes from photosynthesis, which creates CH2O, which is something like, a leaf or some other kind of, biomass, and then oxygen. And the oxygen escapes to the atmosphere, and then a tiny fraction of all the leaves and stuff that grows gets buried in the earth and sort of preserved. And so in this way, the biosphere has sort of like charged itself up like a giant battery with, you could just have a battery with one pole up in the air, another pole down in the food or in the, the coal and get energy out of that. That's what we do. So the amount of energy we use is like 50 times as big as our own metabolic energy. So it's like we each have 50 slaves that are like pumping away on Peloton bicycles on generators to keep all these lights running. And we don't even think about it, but it's ongoing all the time. And in fact, it's more than just keeping the lights on. We actually eat this energy. We have been using fossil energy to fix nitrogen. So take nitrogen gas from the atmosphere and turn it into fertilizers. It's a very energy-intensive process called the Haber-Bosch process. And so you can kind of imagine half of humanity, the nitrogen in our proteins was manufactured in a vat someplace in this really high energy kind of a thing. So when the carbon is released to the atmosphere, a number of things happen to it that we're going to sort of walk through. One is that it dissolves in the ocean and takes part in this absolutely wondrous CO2 buffer chemistry reaction. I can't explain why, but there are, people among us, myself included, who find this reaction just completely captivating. I still remember when I first saw this in a class in college, the angels were singing, ah. And there's a kid in our department who actually works for Kale who's similarly afflicted. He's just bonkers for this carbon chemistry. It's just really beguiling somehow. It's the same chemistry as in our blood because we come from the oceans. So it's complicated, but you can sort of simplify it in terms of just writing that chemical reaction there with the double-headed arrow. That means it's an equilibrium reaction that, the two sides, it distributes the chemicals to one side or the other to find the state of lowest energy, like a dead battery. It doesn't store energy. Some chemical reactions just don't happen, like we don't all spontaneously human combust here, thankfully, because that just is kinetically inhibited. But this is a fast reaction, and equilibrium reactions like this, there's this idea called Le Chatelier's principle that lets us sort of think about how it works. And the principle is that if you put some stuff on one side of an equilibrium, it'll move a little bit to the other side to sort of compensate for it. So when we put CO2 in, it shifts the reaction to the right and makes the concentration of the CO3 2-, which we call carbonate ion, go down. So the two are like, opposite seats on a seesaw. One goes up and the other goes down, and that's how the chemistry of the ocean kind of absorbs this carbon dioxide. And then another thing that happens is that there's all this calcium carbonate everywhere. There's lots of carbonate limestone on land, like around here. It's crazy with limestone from the Silurian period, actually. Or there's also little limestone shells at the bottom of the ocean in the sediments that are kind of accumulating. And so if you take calcium carbonate and you dissolve it, you get calcium, Ca2+, and then you get some of this carbonate ion, the CO3 2-. And so that tends to push the CO2 kind of back down a little bit, by the same sort of teeter-totter sort of mechanism. So the first process, dissolving CO2 in the ocean, takes a while because it's a big ocean and you have to wait for the overturning circulation of the water, which takes like 1,000 years or something like that. This reaction here with the limestone takes even longer. We're talking maybe 10,000 years, something like that. Sort of a long time. And then on longer time scales, we're pretty sure that there's a thermostat mechanism that kind of regulates the CO2 concentration in the atmosphere on some kind of long time scale. We think that because we know what the CO2 concentration was going back through time by measuring the gas in little bubbles in ice cores. And there's lots of little wiggles I'll show you in a second, but if you just draw through the wiggles, it's flat. And if there was any sort of imbalance between CO2 coming out of the Earth and going into the Earth, the CO2 would be going up or down or something like that. So we know it has to be in balance to a very high precision, like it's less than 1% out of whack or something over some kind of long time interval. So the way it works is that there is carbon dioxide that is released to the atmosphere naturally from volcanic gases and in hot springs that have a lot of dissolved CO2 in them at mid-ocean ridges in the ocean, for example. And that CO2 ultimately finds its way back into the solid Earth by way of dissolving a component of crystalline rocks, igneous rocks, like that froze from magma or lava. So there is a component of rocks that is this calcium oxide, and then there's also silica and sodium and other oxides mixed together to make minerals and rocks. But this is like one chemical component of rocks. And when it dissolves, it takes a CO2, ultimately packages it as a calcium carbonate that gets buried in the bottom of the ocean maybe, and then ultimately this calcium carbonate might go down a subduction zone, go someplace where it's really hot, and cook the CO2 back off again, sort of remanufacturing igneous rock and completing the cycle of the CO2. So what makes this a thermostat is this weathering reaction, which requires water. If you don't have water, you can't dissolve rocks. And when the climate gets warmer, you have more water washing over the rocks, and so you have a higher rate of weathering. So the whole thing kind of ends up acting like, I always tell the students, like a kitchen sink where you turn on the water and the water level in the sink maybe rises a little bit if your drain is not really all that clear, but it's going to rise to the point where you've got enough gravity pushing water down the drain that it comes to the equilibrium. So the water going down the drain is the same as the water from the faucet. And if it starts out too low, it'll rise to that level. If you dump 5 gallons of water in the sink all at once, it'll be higher than that, but it'll come down to that level again. So it's a negative feedback kind of a mechanism. So that is not to say that Earth's climate is always, it's like a thermostat, but people keep adjusting the set point, not people, of the thermostat kind of up and down. Actually, what adjusts that set point is plate tectonics, and you move some easily dissolvable rocks into a wet place. They'll dissolve really fast, and that's like turning down the thermostat a little bit. And then there are also, the set point is not perfectly steady, but it helps explain a problem in earth science called the faint young sun paradox, which is the fact that that stars get brighter as they age. And the astrophysicists who kind of own this room, they're not backing down on that. We have to deal with that. And yet, the temperature of the Earth has been sort of, there's always been liquid water pretty much, except for a few colorful exceptions called snowball Earth that didn't last for very long because the thermostat corrected them. But when you look at in more detail, there's kind of like times when the climate is much hotter. They call it hothouse climates. Like if you go to the Field Museum, the dinosaur dioramas, you never see ice there. There was no ice on the planet at that time. The whole planet was considerably warmer. And then there are these periodic kabluis when a lot of these mass extinctions, a lot of them were caused by huge amounts of CO2 actually coming out of volcanoes. That happens more slowly than we're doing it, but you get, like if Yellowstone were to turn into Mordor and start spewing stuff for 1 million years, that's kind of what we're talking about in these large igneous provinces. So I can highly recommend, if you're interested, this book, sort of a pop science book on sort of paleoclimate and mass extinctions called Ends of the Earth by a guy named Peter Brannan. So here was an example of a climate excursion that happened 55 million years ago, which looks a lot like the global warming climate event is expected to be. We have time is going from left to right. No, from right to left here. Paleoclimate people are sort of dyslexic somehow. They keep switching time this way, that way. You have to watch them. But there was this sudden change in the isotopic composition of the atmosphere and the ocean of the carbon, which is totally like what's happening today with the fossil fuel carbon. We see this change, the same change in the amount of C13 and C14 in the atmosphere because we're adding all this weird carbon to it from fossil fuels. So it came out in a spike. We're not sure where or exactly how much, but planet warmed up quite a bit. Actually, it's hard to explain how much it warmed up given how much of the carbon spike there is. Something there's some tension there, but it warmed up, and then both of those sort of recovered over sort of 100,000 years or something like that. So that's one possible constraint on how fast this thermostat might work. But then there's also been these crazy glacial, interglacial cycles that have shaped so much of our world. You know, they gave us the Great Lakes. Those are basically big ice sheet puddles. Like, you know, if you see a place where a deer slept in the snow, you'll see this big circular thing. That's what Lake Michigan is like, only it was an ice sheet. So the ice sheets came and went kind of on a 100,000-year rhythm. So here's us, and here's the last glacial maximum, and you know the temperature and the amount of ice on Earth has kind of been going back and forth between these sort of two states for the last couple million years, and the CO2 has been going up and down in synchrony with that, for reasons that are still mysterious. You know, we discovered these 20-some years ago when I was in graduate school. Everybody was going to figure out what was going on with this and be famous, and now we've all given up because it just doesn't quite make sense. But anyway, the canonical estimate for how long it takes for this thermostat to work, which I don't think we know very well, but the one that everybody cites is this one paper from the 80s who kind of pulled it out of the air, of 400,000 years is the time constant for that. So it's long enough that these glacial, interglacial fluctuations are kind of like, you know, faster than the furnace and the thermostat can regulate them away. It's like you have your house, and then occasionally the sun shines in and warms it up higher than the thermostat setting, and then it cools back down. But the furnace is not fast enough to, you know, make that go away. So anyway, very long time for, you know, the biosphere to clean up our fossil fuel CO2. As far as we're concerned, with our tragically short lifetimes, the CO2 kind of accumulates forever, really. So a kind of schematic of how the system behaves if you just dump a spike of CO2 in the atmosphere kind of instantaneously and then just let it go. It will dissolve into the oceans on, you know, some time scale of centuries or 1,000 years or something like that. And that takes it down to, I mean, the ocean ultimately would take up about 3/4 of the CO2. It doesn't take it all. If the ocean was infinitely huge, it could take it all, but it doesn't. Even though there's a lot more carbon in the ocean than there is in the atmosphere, the number is about 3/4, how much it'll take, but it takes a long time. And then when you react it with calcium carbonate as a sort of antacid, that pulls the CO2 down a little more so that what's left is only like 10% maybe of how much we burned, sort of after 10,000 years. But then that 10% is going to stick around for, you know, something like this 400,000 year thermostat sort of time scale, plus or minus, you know, don't really know. So this is what we call the long tail of the carbon dioxide. So when you put it together and run it in a more detailed, you know, simulation than the sort of cartoon I just showed you, it sort of looks like this. This is the CO2 concentration in the air from 20,000 years ago. This is from the last ice age, and then it rose by that much to give the glacial climate, you know, from like 200 up to 280 or something like that. And then here is the Holocene. Our whole, you know, civilization and agriculture kind of lives here. And then here's, you know, today, with the CO2 going up, and then various scenarios for how much is ultimately going to get burned. Yes, sir?
This tells me that for the point we are now, the tail, we won't recover from this until the year 20,000 AD of the last wave.
Or the year, 500,000.
Well, that's the way in,
Yeah.
but it went down about 20,000 will be back.
Well, I mean, so this is showing us 10,000 years here, and
Still way up.
yeah, it basically just ratchets up to a new normal and stays there forever. There is a little bit of an initial spike of the CO2 that kind of goes down as it goes in the oceans and the carbonate and stuff. But it's kind of, well, in this there's no ice sheets and orbital variations that gave us all the complexity of the ice ages. So this is just a somewhat simplified thing here. I have actually thought about we might be canceling the next ice age, but that's another story. So the temperature kind of just mostly ramps up to a new normal and stays there mostly kind of forever. Here's the temperature. It does the same thing, except you don't have as much of a spike, and that's because during the time when the CO2 is trying to get its way into the ocean, there's all this heat that is going into the ocean because we have to warm up the ocean, and that takes a long time. So that's kind of cutting the head off of the temperature peak that we might have had. And so the temperature is even more like that, more like a ratchet, where it just goes to a new normal, and that's it. One thing that you won't hear much is about the ultimate change in sea level. You always hear about sea level to the year 2100, but it takes ice sheets a lot longer than that to fully respond. So here we're looking at, thousands of years for sea level to rise completely, and ultimately it could be like 50 meters higher than today. So by 2100, it's like, a meter or something. But the only reason we care about 2100 and not the year, 5000 is because we're going to be gone and we don't care. But it's not like the intrinsic time scale of the problem at all. So here's a correlation plot of sea level in the past plotted against temperatures in the past. So last glacial maximum, it was like 6 degrees colder and sea level was 120 meters lower. Hothouse climates, maybe tens of meters higher. And so, there's a whole lot of complexity here, but you can also just connect the dots and see that line. And this is the forecast for the year 2100, and it's off the line because we're not giving it time to get on the line. So it's a real kind of degradation of the biosphere. This shows places that are especially hit by sea level rise. So the American Gulf and East Coast and Florida is on the top 10 list. This shows how much area of land, what fraction we lose with that much sea level rise. So just in terms of the total area, it's less than 10% of the area of the Earth, but in terms of where people live, maybe 25%, and where the crops grow, there's all these low river deltas that are very fertile, that are kind of going to get flooded. Okay, so here's a plot of where the fossil fuel CO2 is now, how it has been evolving through time. So the red curve is the cumulative emissions of carbon, how much we have released, and the black curve here is what's in the atmosphere, which is less than we've released because there's a bunch, this blue line here has dissolved in the oceans. So like order half or something. The oceans have like helped us out. And then the land is interesting. So the land was a source of carbon for a long time as, it's called the pioneer effect. It's deforestation, like around here and other places in the temperate world, cutting down a lot of trees. We're not cutting down trees as quickly. In fact, there's like tree regrowth in the temperate latitudes, but there's still a lot of deforestation happening in the tropics. But this green is the net from land, and there's some kind of a mysterious uptake of carbon that is helping us out, that's compensating for the deforestation. And it's a huge amount of carbon, and it's kind of astonishing to me that we can't actually find it. It's like there's as much carbon as all the mass of all the people on the planet that goes away someplace every year, and it's hard to find because the carbon in soils is very heterogeneous and hard to, it's just a hard thing to track. But, so the land has been sort of helping us out. So this plot kind of summarizes a couple of things about the carbon cycle. We have the atmosphere is kind of a grand central station. Everything communicates through the atmosphere. There's carbon that goes back and forth between the solid Earth at a very small rate of about 0.1 of these gigatons per year. That's very small compared to how much dissolves in the ocean in one place and comes out of the ocean in another place, all the time, which is about 90 gigatons per year. And then, the trees grow and then the leaves decompose. There's a huge seasonal flux of carbon in and out of the land surface as well, which is also order 100 gigatons a year, like 1,000 times greater than these fluxes to the solid Earth that, are the thermostat. And then we can also see the sizes of the various reservoirs here. It's kind of important. So the atmosphere has about 700 of these units, billion metric tons of carbon. The land, all the trees and stuff, and the grass, all the living carbon that we can see is actually somewhat less than that. So, let's say we put thousands of gigatons into the atmosphere and then try to plant trees to make it go away. There's just not enough room for that many trees because the tree reservoir is just not really that big. There's a bunch of carbon stored in the ocean, but most of the carbon on Earth is in the solid Earth. So this is like the big difference between Earth and Venus. Venus, they really didn't take the garbage out. All the carbon is in the atmosphere. It's like 70 atmospheres. It's more like a supercritical CO2 ocean than an atmosphere, really. So planetary housekeeping, very important. So fossil fuels, the canonical number for the worst case scenario, like in the plot I showed you of the climate model, is about 5,000 gigatons of carbon. Most of that is in the form of coal, and when they calculate how much coal there is, the question is, how much is there that would be profitable to dig up? And so it's a very complicated question about how much energy costs and mining technology and things like that. So this is a super fuzzy number, and it would take a few hundred years actually for us to burn that much, but that's kind of just what's taken as a worst case scenario. And it is kind of bad because 5,000 gigatons is a lot more than 700 gigatons. So it's a lot of carbon. So what would it take to clean it up? This is a screenshot from an online model that I wrote to use to teach undergrads about all this stuff. And you can use these boxes here to adjust, the rate of CO2 emission and land use carbon change and stuff. And so what I did is I said, okay, at 2025, we'll go cold turkey. So I set it to 0. And then also, we will start to pull CO2 out of the atmosphere, initially at 1 gigaton per year, and then ramp up to like 4 gigatons a year, and then kind of ramp back down again. And I was tweaking it to try to get the CO2 concentration, which is here, to kind of come in for a landing at a value of 350. So maybe you've heard of 350.org and Bill McKibben. That number comes from the amount of CO2 in the air that would restore the energy balance at the top of the atmosphere so it would stop any further warming. It's been a couple decades, so it could be that the no more climate change value might be higher than that now because temperature is warmer. But anyway, just taking 350 as a benchmark, I tweaked those CO2 uptake rates until it sort of came into a landing at about 350. And it takes decades to get there. That's kind of an important thing. So when you add up the amount of carbon that I took out of the atmosphere, it comes to about actually 150 gigatons of carbon, which is less than I had expected, actually, given that we've put about 500 gigatons in. But it turns out that the carbon that dissolved in the ocean, by rights, it ought to come back out. It's just a buffer. But it turns out that in this kind of simple model, it doesn't really very much. So that's kind of like a freebie. And we don't necessarily have to try to get it back to the natural value of 270. 350 would be a lot easier. So we're saving a lot of, we don't have to pull out the whole 500 gigatons to get something that seems like progress. But now, here comes the pickle. So Cale and I are prepping a class, a new undergraduate class to teach in the spring about carbon removal. And we're going to show everything that I showed here today to reveal just how big a pickle we are in. We are in a real pickle because it's going to cost a huge amount of money to clean this up, and there won't be any climate benefits for, decades. So, that's kind of a hard sell. But here's how it breaks down. The total amount to clean up from the last page was 150 gigatons of carbon. So as soon as you switch hats from a geochemist to a money person, they change the units, and they do it per ton of CO2 instead of per ton of carbon. Actually, if we did this according to the higher principles of chemistry, we'd be counting atoms and doing moles, because then a mole of carbon is 2 moles of oxygen instead of all this mass bullshit. But we're stuck with it. Somehow we lost control of the conversation. And so now, if we want to think about money, all the figures are in terms of weight of carbon dioxide instead of weight of carbon, and that's like more than 3 times as much because of the weight of those oxygens. So 150 gigatons of carbon turns into 560 gigatons of CO2. And then, we'll hear more about costs from Cale, but a rough number that is not like shocking, it's actually kind of pretty good, is maybe $100 per ton of CO2. And I looked it up for the cost of solid waste. It's about that also. It depends on where you are. It's a lot cheaper in Idaho than it is in Massachusetts for some reason. But $100 a ton of garbage is not kind of unreasonable. So we here in the US kind of almost invented the high carbon lifestyle. And so we are kind of way out ahead of the rest of the planet in terms of how much of a mess we've made. We're like 5% of the population, but we've released like 25% of the carbon. So, if fair is fair, 20-some% is our share of how much of a mess has been made. So that comes to a total of, if I did my math right, $12 trillion to clean up the mess. So that's on top of the cost of going cold turkey to emit no more CO2, which I have no idea how much that would cost. A lot. Or if we don't go cold turkey now, we'll emit more CO2. We'd have to pull more CO2 out. So this is like an absolute minimum CO2 cleanup cost under ridiculously oversimplified conditions. But per person, each of us, $33,000. And we are going into the hole at a rate of about $1,300 per year. That's a pickle. That's a real pickle. Plus, there's going to be this compound interest from natural carbon sources. So the poster child is these permafrost deposits that in places where they weren't sort of scrubbed off by ice sheets, there was all this deposition of glacial flower and grass that grew there and then froze. So all these frozen grass roots, 1,500 gigatons of carbon in permafrost that we expect when the permafrost melts in a couple hundred years is going to get oxidized and release CO2. Maybe even methane, depending on how soggy it is. So it's going to add to our burden. Just as a public service announcement, I'm compelled to point out that the permafrost carbon also contains a whole lot of mercury. So mercury is another forever issue like CO2 that it gets released by burning coal or mining for gold or something, and then it just cycles around in the biosphere and continues to poison our seafood for thousands of years. And it's in contrast to CO2. Half of the CO2 is in the atmosphere, but the fraction of the anthropogenic mercury that's in the atmosphere is like 1 or 2%. There's just no way you could even talk about cleaning up the mercury. So, CO2 is not so bad. Another forever issue is this PFAS, these Teflon chemicals. They might continue to cause developmental disorders for millions of years. So this is kind of a word cloud of all the stuff we're going to hear about from Cale in a couple of weeks of different ideas that people are thinking about. You can just scrub CO2 out of the air like they do in a submarine or a spaceship. There's a great scene in the movie Apollo 13 where they're trying to figure out how to save Tom Hanks by doing that. Then you have to somehow do something with the carbon dioxide, so squirt it down into the earth or react it with something. Rock weathering is the basis of that CO2 thermostat, and it takes way too long, so it's not really all that helpful to us. But maybe we can make it go faster by grinding up basalt and sprinkling it on playgrounds or something like that. Or maybe we can grind up basalt or get some other kind of base and sprinkle it over the oceans. And then that changes that CO2 chemistry of that buffer system. You make the CO2 go down, and so more of it comes back into the atmosphere. We just heard a great talk about a guy at Woods Hole who did that experiment. They put a bunch of base into the ocean. It was a nightmare to get permission to do that, I guess. But they have all the data they need to figure out how well that works to pull CO2 out of the air. All the scenarios for the future where people claim this is how we can make it work without, crashing and burning, seem to rely on this biomass burning energy with carbon capture. So you grow something that grows fast like switchgrass, and then you burn it and capture the CO2, so you get energy and you get the CO2 because the switchgrass pulled the CO2 out of the air. Trouble is there's not enough farmland to grow that much switchgrass, but there's like this disconnect. All these people are working on it, and yet it just doesn't seem like it's going to be all that helpful. And then here's another one, ocean iron fertilization. So if you sprinkle trace amounts of iron in some parts of the ocean, you get a bloom of phytoplankton. And when this was first discovered, a long time ago. I remember the guy who was giving this talk about it said, "Give me a tanker of iron, I'll give you the next ice age." But it turned out you can make a bloom, but it doesn't translate into carbon that's being pulled out of the atmosphere or even out of the surface ocean, because it just kind of recycles in place. And so it's not the magic bullet that we thought it was. Biochar, there are a lot of people who are super enthusiastic about biochar. You take some wood and sort of, char it, heat it up without oxygen, make charcoal, and it will last forever in soils, and it's really good for holding, nutrient ions and things, and holding water. So there's all kinds of benefits of that. But, whether you could do that enough to save the world is kind of like, I don't know. Planting trees, planting kelp, artificial ocean upwelling, all kinds of really delicious, wacky ideas that we can hold Cale's feet to the fire to say, what the hell are you talking about? How could this possibly work? Anyway, so that's what I brought to show you, and we have lots of time for questions, and I hope this has been useful. Thank you. Yes, sir.
These reactions that affect the carbon are temperature control. Now, if we compare today where we have the results of the Industrial Revolution and now the use of nuclear energy, my specific question is, does the use of the Industrial Revolution and the nuclear energy, the way it affects the water that we use, the fresh water that is eventually discharged in the ocean, is that significant enough to affect those reactions? That's my question.
The question is, correct me if I'm wrong, whether the waste heat from nuclear power, if we discharge that heat, hot water into the ocean, it would tend to make CO2 degas, but I haven't ever heard of that as a significant thing, really. Nuclear, has a very low carbon footprint, but one of the ways that clarifies options going forward is to project how much carbon-free energy we will need by, say, the year 2100, if we want to keep growing and having energy, but we don't want to destroy the climate. And so how many, petawatts of power does it take, by this option or that option, to fill in that gap? And if you try to do it with nuclear, we'd have to build like a new nuke plant on the planet like every week for the next, decades. And that just, it's just a scale problem. So, there are climate scientists for whom I have great respect, like Jim Hansen, who's a visionary guy who's very enthusiastic about nuclear power, but I don't personally share that because I just don't think it's enough. And then, you get these waste that lasts forever, and it just seems like, windmills are not as nasty. But does that answer your question?
It gets close. I was particularly concerned about the temperature
Yeah.
of the fresh water that's discharged.
Yeah, I know. I don't think that's a huge thing. It does, you're right, it would tend to degas CO2, like a warm Coke is going to degas. But, there's just not that much, it's just a drop in the ocean, I would guess. Sir?
I'm going to introduce myself. I used to work at Abbott Planetarium and also at the CERN Kearney Space Center.
Mm-hmm.
So I'm an astronomer and therefore a graduate. Anyway, I have a bunch of questions, but the first one I'm going to say is, why for all the urgency that's out there, is nobody talking about space-based solar?
Oh, I have heard about that as one of the options for, filling in the gap to the year 2100. There's this really visionary paper that goes through these different options. And, I guess there's one company that's talking about putting solar panels, in orbit. And then there's another that I read, they had a whole business plan about manufacturing solar cells on the moon, kind of out of lunar soil. And there's no clouds and no birds to poop on anything. And so, then you can beam the energy back as microwaves, and it doesn't apparently fry birds in the air or airplanes fall from the sky or anything. So it is something that people talk about.
Best way to do it would be to have those panels on both the eastern and western limbs of the moon. So no matter where the shadows of the moon itself are at,
Yeah.
there's always going to be plenty there. And also place them at the branch points 4 and 5
Hmm.
around the moon. And that way you would have, if each spot had 50% of the capability of empowering the Earth, then no matter what, where the Earth's shadow is, or what the situation is with the horizon problems of the moon, you would always have at least 100%
Yep.
available. And most of the time you would have 150% available.
I'm sold.
That power could be used to say, take stations along oceans that could then do desalination and pump the water to where it's needed.
Mm-hmm.
And also have hydrolysis, create hydrogen fuel. So we could have all that, and why don't we do that?
Cool. Anybody? Yes, sir.
Yeah, concerning the long tail,
Yeah.
like the estimated 400,000 years, what is the mechanism to get rid of that?
The mechanism to get rid of it, to
Yeah, because it doesn't last forever. So how does it eventually get out of the atmosphere after that 400,000 years that it's estimated to stay in there?
yeah. So during that time, yes, I would. Thank you for the reminder. I can never remember that for more than 2 minutes. I'm just such an idiot. Yeah, the question was, where does that tail go? And during the time when that tail is there, there's it's a warmer climate than it would have been, and so there's more water washing over the rocks and more CO2 being removed from the atmosphere than is coming out of the volcanoes. And so it's like the water level in the sink is higher, and so it's going down because it's going down the drain faster than coming in from the faucet. But then, it reaches the steady state where the fluxes balance, and that's when it's done. Welcome. Yeah.
We measure the temperature in the atmosphere, and this is how we measure the temperature that we're talking about. How about the temperature inside Earth? Does it go up the same way as it goes up in the atmosphere?
What a great question. Yes, I think, not enough to worry about. The question, the question, it had been 30 seconds, I'm sorry, it had slipped by. The question, the very interesting question, is whether there is sort of global warming inside the Earth. So I guess theoretically, there's a lot of heat coming out of the Earth, and then there's this surface boundary condition, which is colder than that because all this energy goes to space, and so the temperature kind of has to meet that surface value, and if you were to turn the planet into Venus or something where you really make it hotter, it seems like that would propagate down into the Earth, just as you suggest. The same thing is happening when they model permafrost dissolution or melting, or the dissolution of these methane hydrate deposits in the ocean. You change the top boundary condition, and it takes time for the temperature to kind of, propagate.
If the temperature is high in the atmosphere, does that mean the temperature is high down?
It gets a little bit warmer theoretically, but not a lot. Actually, there was a paper about what happens to the temperature under the ground when you build a building and heat it all winter long. So this was like subsurface global warming, they called it, and a reporter asked me about it. I said they were just riding coattails because, it had nothing to do with global, but, it is possible to, perturb temperatures in the deeper Earth. Reading this paper about warming under buildings, it wasn't obvious to me that this was something I was going to lose sleep over exactly, just more of a curiosity. But there's also warming of the deep ocean that is kind of driven by the climate of the surface. The deep ocean is filled with cold water from the high latitudes, and so you make the high latitudes warmer and the whole deep ocean gets warmer. We see that in the geologic past. Yeah.
Two questions. What about all the bombs that have been going off in all the wars, the recent wars? How does that affect the atmosphere?
Question is about nuclear weapons tests and I guess. Well, I don't know about regular bombs, but the nuclear weapons test left a delicious signal of carbon-14 in the atmosphere that is really useful for figuring out ocean circulation and stuff like that. It's still, it made all this carbon-14 and it's still kind of making its way into the system. And then there's a question about if we blow off a bunch of bombs in the future, putting smoke up into the stratosphere and causing nuclear winter, which would last for a long time and be a bad thing. But, just the conventional weapons, I haven't heard about them having a global climate impact.
The other question, you mentioned heating the ground underneath, but we're building ovens, cities, highways, the sun heats all that.
Yeah.
It acts like an oven. How much does that affect the overall?
So this question is, I guess, about what we would call albedo changes due to land use changes. So this is definitely a thing that affects local climate in like cities. Like if you look at a temperature map of Atlanta, it's just always this ugly hot blob compared to the surrounding area because you have all this cement that absorbs heat rather than plants that evaporate water and get rid of heat. So it's not clear that that urban heat island effect is changing the global temperature all that much. But we do have to be concerned if we're trying to figure out how much warming there has been that we want to attribute to CO2 in the atmosphere. If it's really the urban heat island effect, we don't want to falsely blame the CO2 in the atmosphere. So it is an issue that that had to be thought about. Yeah. Yeah.
Basic clarifying question.
Please.
Talk about the relationship between like seasonal fluctuations of emissions and longer time scale. Like, are the sort of seasonal fluctuations are less of a problem because of the time scale of temperature response?
The seasonal fluctuations.
Yeah, you were mentioning like trees growing and the leaves falling and this.
Oh, yeah.
Are we not sort of thinking about that in terms of the longer scale of carbon in the atmosphere because of the differences in this time scale versus temperature response?
Yes, but trying to figure out, question was, the seasonal cycle in carbon fluxes, like in and out of trees, how does that project onto longer timescale things that we might be interested in? The first reliable measurements of the CO2 concentration in the atmosphere were made by a guy named Charles Keeling, and he did this on Mauna Loa to have it be on a mountain in the middle of the most remote, part of the atmosphere we could get to. But there's this huge seasonal cycle that comes from, CO2 coming in and going out. And it's opposite in the southern hemisphere because the seasons are opposite, and it's bigger in the northern hemisphere because there's more land in the northern hemisphere. It's just gorgeous to watch. I have this little animation of I can maybe try to dig up. Well, it'll take too long and demonstrate my ineptitude with my laptop. But it's like the biosphere breathing. It's really sort of gorgeous to watch the CO2 going up and down. It doesn't really affect the long-term picture all that much, but trying to figure out, for example, where the missing, what they call the missing sink, how is the land surface taking up all this carbon that we can't find? Trying to trace that by figuring out which way the wind is blowing and what the CO2 concentration is, and figuring out where there's holes in it or whatever is complicated because you've got all this other stuff going on. One more question.
How do you compare the amount of CO2 that humans put out compared to natural processes like volcanoes and things like that? What's the difference between the two?
So the natural rate of CO2 emission from volcanoes, which is presumably, the question was, how does the natural fluxes of carbon compare with the human fluxes of carbon? Very astute question. So we are burning about 10 gigatons a year, which is smaller than the breathing of the biosphere, which is 100-something gigatons a year, or the sort of cycling back and forth to the ocean, which is also like 100 gigatons per year. But those are back and forth fluxes, so they're not really comparable. The one that we would want to compare to would be the flux of carbon going back into the solid Earth as part of that CO2 thermostat. And that is about 0.1 gigatons a year, so 100 times less. So we're kind of blowing the budget by like a factor of 100, basically. Okay, another question.
I noticed that on November 1st, it's going to be about geoengineering projects like block the sun.
Yeah.
If you want to see what might happen, should that get out of hand, there's a 20-year-old documentary that's recently been available on YouTube called The Year the Sun Turned Black.
Oh, yeah. Yeah, there's a book. Yep.
Of course, every second of it's an hour and 39 minutes. The Year the Sun Turned Black.
Yeah, you don't want to overdo that. No, there's lots of examples of that kind of thing.
Real out of hand.
Yep, yep. Yes?
There's been a lot of communication about the energy demands in the creation of artificial intelligence projects.
Yeah.
Is that being considered in regard to the increased negative impact on climate's warming?
Is that being considered? So the question was, I'll get the hang of this, whether all the computation involved in artificial intelligence that's all in the news everywhere these days is like part of our thinking in terms of, projections going forward. I am not like a specialist in like forecasting the future, but I can say that there are these scenarios that were put together, to talk about this stuff that had various levels of, what's going to happen. There was a business as usual scenario, and then there was a, we'll clean ourselves up somewhat scenario, or, the best possible drawdown scenario. And pretty much we've been following the business as usual, like, no real action kind of projections.
But the question really is the amount of energy
Yeah,
that's
I know.
needed to
Yep.
drive these units.
Yep.
That energy is going to produce additional carbon
Yep.
emissions, right?
Well, there's all kinds of things that produce carbon emissions. So we can't just stop using AI and fix the problem. We also have to not manufacture things or go anywhere or eat any food it comes from all kinds of different things. And yeah, it is a big acceleration in energy use. That's true. Okay, one more. Well, fixed is kind of a strong word. It's already screwed up. But yeah, I get this question from students, and they always ask, and the question was, how optimistic am I, that we will succeed or not succeed? And my feeling is that that's kind of a binary question. Like, it's not like, oh, we failed, Greta Thunberg is unhappy with us, so we'll just reboot, turn off the machine, and there will be a future, and there will be people in it. The question is, how much are they going to be angry at us for screwing things up for them, in a way that's really hard to fix? And, I'm not particularly optimistic that we're going to, do the best job we could do on that. But you all are here, and that gives me hope. So thank you for coming.